Hello, I'm Chris Athanas. I'm a KMP developer, and we're going to be continuing a series on hardware. Tech support said they're going to be coming out Tuesday to fix that, close that thing down. We'll see. Not holding my breath. Okay, so we're gotten on past the tube. Now we're going to the transistor. The big idea. Instead of using an electrically heated wire, like in the tube, to control the flow of electricity, it's the grid. You know, changes the does the control, but the heated wire gives off the electrons, and the grid stops them or lets them go. The gate to control electricity. We can use an economical semiconductor material to reduce the size factor of. I said 100. I meant 100,000. 100,000 times smaller. I fixed it. Tubes have a very similar behavior transistors have a very similar behavior as the tube, but they're a lot smaller and a lot faster for switching on and off. So let's look at this video here. Oh yeah, here it is. This is from Ben Eater. We're going to be looking, if you really want just a full course on digital electronics and you want to understand how the computers work from the very bottom to the very top and the exact how it all is put together. Ben Eater does what I'm doing, except he goes into implementation details on the actual hardware, digital electronics. And if you follow his course and you do his exercises, you will know 100% how this stuff works from the bottom to the top, like in detail. So his is the best. You don't have to go to college. Don't have to do that stuff. If you do go to college, his course will probably be easier to understand and actually functional. And Ben Eater is a god among men in my mind, because just how he can teach so well.
So this right here is a bipolar junction transistor, which is a pretty common kind of transistor. And this particular one is an NPN transistor. And so this transistor is made up of 3 layers of silicon, like this. And maybe you can guess what it means for it to be an NPN transistor. These 2 layers of silicon are N-type, and this layer here is P-type, NPN. And if you haven't watched my previous video where I go into quite a bit of detail about what these N-type and P-type silicon is, you should definitely go back and watch that. Otherwise, the rest of this isn't going to make a whole ton of sense.
It just means these are more negatively charged. These are more positively charged. But this is a semiconductor material. When this thing goes, is because it has a correct charge process, it allows current to flow through. When it doesn't, it likes to stop. It's the same thing here, where it's the emit. This is the cathode, the little light in the tube that's emitting things here. It's going backwards than the symbol. Thank you. It emits, but the labels are correct. The symbol is the reverse of actually what the electron's doing. It's real. Okay, so it emits here, goes through here, and this base is the gate, the gate. Okay, and that controls whether it's on or off or somewhere in between. And this is the collector, so it comes around here. So this is the load is on this side again, and the control is this area here, which you'll get into. So that's what's going on.
And so this is an NPN transistor, and they make PNP transistors as well, but we'll just talk about NPN for now. And so this here is the circuit diagram for a transistor, and it's got the 3 leads coming off of it. There's a emitter, a base, and a collector. And if you look at the actual physical transistor, there's 3 leads coming off, and this is the emitter, the middle one is the base, and this is the collector, although that's not really standardized, but in this particular case, that's how it works. And what a transistor does is it is a current-controlled switch. And so what that means is that if we establish a small current from the base to the emitter in this direction, the transistor will switch on, and it will allow a very large current to flow from the collector to the emitter. And sometimes you can also use this as an amplifier, because a small current is amplified into a large current flow here. And so first off, there's actually something kind of confusing about the way this diagram is drawn with this arrow like this, which is that in a circuit diagram, and a lot of times a lot of engineers like to think about positive current flow, which is current flowing from positive to negative, when in reality it's the electrons that flow from negative to positive. And it doesn't really matter which convention we use, because as long as there's current flowing in one direction or the other, the current will have the same effect. But when we start to actually look at what's going on inside the transistor, it's easier to think of this in terms of the direction that the electrons are flowing instead of the conventional direction.
Exactly. He brings it right up because it's so like God.
So really what's going on in here, even though the arrow is pointing this way and we think of current flowing that way,
not confusing at all.
In reality, the electrons are flowing from the emitter to the base. And so we'll just turn all this around for this discussion here. And so to kind of restate what it is that the transistor does in terms of electron flow is that a small flow of electrons from the emitter to the base will turn the transistor on and allow a large flow of electrons from the emitter to the collector. So if we look at it in this scenario,
so it's the same thing as this relay, right? This is the base or the grid. This is controlling this other large current flow, 330 volts. This is like 9 volts that's controlling our little relay. And it's the same thing with the tube. this filament emits the negative electrons trying to get through the grid or the base to the plate. All right, that's how it works.
Piece of N-type material might be the emitter. This middle P-type is the base, and then this N-type material over here is the collector. And so what we're going to do with the transistor is that we're going to try to put a bunch of electrons in over on this side, and we want to get them out over on this side. But if the transistor is off, then we're not going to get that current flow. And in order to turn the transistor on, what we want to do is get a small current flowing through the emitter and out the base like this. And once we get that small current flowing, then the transistor will turn on. We'll have a large amount of current able to flow all the way through it. So let's redraw this so we can kind of get a closer look at what's really going on in here. So if we take a closer look at what's going on here, we've got the emitter here, which is N-type material, and so we have these extra electrons that are in here that are free to kind of move around. We've got the base, which is P-type material, and so we have these holes that are in here that are free to move around. And then the collector is also N-type, and so there's electrons that are free to move around. But at each of these PN junctions, remember we have this depletion region, which I've kind of exaggerated here. We have this depletion region because the electrons from the N-type material are going to fill in some of the holes in the P-type material and kind of neutralize each other. And so there are no charge carriers in these depletion regions in here.
And you can watch the other videos to go into that detail. But yeah, I just want to show you that his first video there. And this is the kind of stuff that he was talking about here. And this is a really great animation I found inside this Verasium video.
Everyone knew that LEDs had the potential
about how LEDs work. And an LED is just one of these things that at the junction where the three wires come, when electricity goes through properly, it actually emits infrared radiation. And they figured out how to make it visible range and visual range, because all they do is they do some mucking about to make it light up so we could see it. But once they did that, it was hard to get to the blues. But the explanation of how they got to blue is a really great animation of how electricity flows through wires.
Potential to replace light bulbs, because light bulbs, the universal symbol for a bright idea, are actually terrible at making light. They work by running current through a tungsten filament which gets so hot it glows. But most of the electromagnetic radiation comes out as infrared, heat. Only a negligible fraction is visible light. In contrast, LED stands for light emitting diode. It's right there in the name. LEDs primarily create light, so they're far more efficient. And a diode is just a device with 2 electrodes, which only allows current to flow in one direction.
So it's still these things are all working the same. You can use a diode as an LED, you can use an LED as a diode. You could use, if they have that base thing in here set up that way, you could use this as a transistor and a light at the same time.
So here's how an LED works. When you have an isolated atom,
stuff.
each electron in that atom occupies a discrete energy level. You can think of these energy levels like individual seats from a hockey stadium. And all atoms of the same element, when they are far apart from each other, have identical available energy levels. But when you bring multiple atoms together to form a solid, something interesting happens. The outermost electrons now feel the pull not only of their own nucleus, but of all the other nuclei as well. And as a result, their energy levels shift. So instead of being identical, they become a series of closely spaced but separate energy levels, an energy band. The highest energy band with electrons in it is known as the valence band, and the next higher energy band is called the conduction band. You can think of it like the balcony level. In conductors, the valence band is only partially filled. This means with a little bit of thermal energy, electrons can jump into nearby unfilled seats. And if an electric field is applied, they can jump from one unfilled seat to the next and conduct current through the material.
So they're using kind of a water analogy here, but this is actually really at the atomic level. This is actually more like what's going on. Yep.
In insulators, the valence band is full, and the difference in energy between the valence and conduction bands, the band gap, is large. So when an electric field is applied, no electrons can move. There are no available seats to move into in the valence band, and the band gap is too big for any electrons to jump into the conduction band. Which brings us to semiconductors. Semiconductors are similar to insulators, except the band gap is much smaller. This means at room temperature, a few electrons will have sufficient energy to jump into the conduction band, and now they can easily access nearby empty seats and conduct current. Not only that, the empty seats they left behind in the valence band can also move. Well, really, it's the nearby electrons jumping into those empty seats, but if you look from afar, it's as though the empty seat or hole is moving, like a positive charge, in the opposite direction to the electrons in the conduction band.
So this is where they get this thing where they say, so we have the conceptual idea of the flow of a negative to positive or positive to negative. This is what they're talking about here. So it does have an explanation. And it depends on your point of view, but this is where they get their terminology between the physical flow of electrons versus the electrical engineering flow of current. How's that?
By themselves, pure semiconductors are not that useful. To make them way more functional, you have to add impurity atoms into the lattice. This is known as doping. For example, in silicon, you can add a small number of phosphorus atoms. Phosphorus is similar to silicon, so it easily fits into the lattice, but it brings with it one extra valence electron. This electron exists in a donor level just beneath the conduction band. So with a bit of thermal energy, all these electrons can jump into the conduction band and conduct current. Since most of the charges that can move in this type of semiconductor are electrons, which are negative, this sort of semiconductor is called N-type, N for negative. But I should point out that the semiconductor itself is still neutral. It's just that most of the mobile charge carriers are negative. They are electrons. So there is also another type of semiconductor where most of the mobile charge carriers are positive, and it's called P-type. To make P-type...
And that's the stuff that Ben was just talking about. Except we have a nice animation. You should go look at his stuff too, because how he explains it's very, very good. But the animation here is very helpful for like, what are you guys talking about?
Silicon, you add a small number of atoms of, say, boron. Boron fits into the lattice, but brings with it one fewer valence electron than silicon. So it creates an empty acceptor level just above the valence band. And with a bit of thermal energy, electrons can jump out of the valence band, leaving behind holes. It is these positive holes which are mostly responsible for carrying current in the P-type semiconductor. Again, the material overall is uncharged, it's just that most of the mobile charge carriers are positive holes. Where things get interesting is when you put a piece of P-type and N-type together. Without even connecting this to a circuit, some electrons will diffuse from N to P and fall into the holes in the P-type. This makes the P-type a little negatively charged and the N-type a little positively charged. So there is now an electric field inside an inert piece of material.
So doing the water model here, where there has to be this is going uphill, trying to go uphill.
Electrons keep diffusing until the electric field becomes so large it prevents them from crossing over. And now we have established the depletion region, an area depleted of mobile charge carriers. There are no electrons in the conduction band and no holes in the valence band. If you connect a battery the wrong way to this diode, it simply expands the depletion region until its electric field perfectly opposes that of the battery, and no current flows.
And that's how a diode works.
But if you flip the polarity of the battery, then the depletion region shrinks, the electric field decreases, and electrons can flow from N to P. When an electron falls from the conduction band into a hole in the valence band, that band gap energy can be emitted as a photon.
Right. So when it falls down here, an infrared, just the way the natural crystals are formed, it comes out infrared photon. So that's why like they didn't know about this activity until they had a way to detect photons coming off it. But all just like, oh, this is interesting. How can we make this better? And it's just been a continuous process of that stuff. LEDs are pretty close to quantum mechanical. You can't get much more efficient. We're approaching that level.
The energy change of the electron is emitted as light, and this is how a light-emitting diode works. The size of the band gap determines the color of the light emitted. In pure silicon, the band gap is only 1.1 electron volts, so the photon released isn't visible. It's infrared light.
These LEDs are actually used in remote controls like for your TV, and you can capture them on camera. Moving up the spectrum, you can see why the first visible light LEDs were red, and then green, and why blue was so hard. A photon of blue light requires more energy and therefore a larger band gap.
By the 1980s, after hundreds of millions of dollars had been spent hunting for the right material, every electronics company had come up empty-handed. But researchers had at least figured out the first critical requirement: high-quality crystal. No matter what material you used for the blue LED, it required a near-perfect crystal structure. Any defects in the crystal lattice disrupt the flow of electrons, so instead of emitting their energy as visible light, it is instead dissipated as heat. So
okay, so it just talks about how he invented some of this stuff. But yeah, so I wanted to show that off a little bit. Maybe if I could find the section here where he has the animation of right here. All right, right here.
This allowed him to use some
just talking about
with electrons, leaking them back into the gallium nitride layers. Unfazed, within a few months, Nakamura had fixed this too, by creating the opposite of a well, a hill. He returned to his...
So he's working through all these chemical layer processes to try and he's just experimenting with all kinds of stuff he can get his hands on before he runs out of money to get this. And his boss is super pissed. It's great to watch this video about how this all happened because it's a very common story and kind of sad.
Reactor one more time to make aluminum gallium nitride, a compound with a larger band gap that could block electrons from escaping the well once inside.
Okay, so he goes into detail about how they made blue LEDs. It's very interesting and useful knowledge. Just knowing how LEDs, when they do that, when they go across that bridge of a diode, it drops down in value, gives off a photon. Well, whoever thought that would have happened, we're just, okay, we can use this for making lights. Yeah, okay. Here's how we're going to use transistors for switching in computers. I love these old movies because they really do describe in very good detail what's going on in a way that scales. The metaphors all scale. But they use plus we paid for it. I was like, if you're a U.S. citizen, you paid for it. Because you're an admin.
This is a transistor switching circuit. It's quite different from any vacuum tube switching circuit. The transistor itself acts as the switch.
I mean, it's not that different. It's just a different technology, a different implementation, right? Still doing the same thing. We're still using one smaller voltage to control a larger voltage. Okay.
This kind of circuit is seldom used for such simple jobs as turning on lamps. It is used very frequently to perform mathematical operations in electronic computers.
And that's what we're interested in.
This film shows some elementary principles of transistor switching in computers. The basic characteristic of a switching circuit is the fact that it has only two possible operating conditions. Here, they are on and off. But any two-state circuit is called a switch, even though it may not be a simple on-off switch.
Right. So just keep in mind, any time you hear the word switch, doesn't mean just a mechanical thing, wires broken apart together. Anything that can be possibly turned off and on by controlling some other thing. That's what a switch is.
This one has two different voltage outputs. The digit 1.
Okay, here we go.
And the other condition,
Wait, here we go.
the digit 1.
Oh, that's right. There's a little clip in the. This part of the thing got clipped.
Of the 10 digits,
Old movie.
only 0 and 1 are actually used in computer design. Therefore, only simple two-state switches need be used. In the off condition, the output can represent either 0 or 1. The choice is arbitrary. In the on condition,
Well, it's not arbitrary. We control it. There's somebody controlling the state. But those are the only, for as far as we're interested in, for computers, it's 0, 1. Even though it does do all the states in between, when it transitions, it doesn't go instantaneously to 1 or on instantaneously. It's just like a little boom, and over time, and it's like it's nanoseconds, but it's like there's a switching time it takes for it to fall and do its thing.
the output, of course, will represent the other digit. This simple switch, used in various combinations, can perform mathematical operations. However, even elementary mathematical operations are too complex to be performed in one-stage electronic circuits. So the operations are broken down into steps. This circuit performs one such mathematical step.
This is the OR. So this is how you use a wire up two transistors to do is it OR or AND? We'll see. I can't.
It is called an OR circuit
Yeah, it's OR.
because it delivers an output if
Series.
either input A or input B is
Yeah.
present. Here's another example. This is called an AND circuit because it delivers an output only when both input A and input B are.
So schematically, you could replace this with one of those tubes, like Transistor 3-input tubes. Same thing. Do the same. It would do the same exact thing. Now, how fast it happens and how exactly it switches from one to the other, that's a little different, which we'll be getting into.
are present. The circuit consists of two switches in series. When both inputs are negative, current can flow in the load. If either input is positive, the corresponding emitter is reverse biased and the circuit through the load is interrupted.
Right. So in this case, a 0 isn't lack of current. A 0 is negative current. So positive current, negative current. Just to make sure it just knows when it's not like floating around. So we'll talk about the floating around if it's unhooked in digital electronics.
By using such
It can be a thing. So they have to actually go to ground, or wired to the negative or wired to the positive. We don't want it floating around. It can cause strange, undesired conditions.
combinations of switching circuits as this and this, complex computer systems can perform in seconds mathematical computations far too difficult to do at all with pencil and paper. Let's see how one switch works, since it's used as a basic building block for constructing computers. The collector output is controlled by voltage applied between the base and emitter. When the input signal, battery voltage here, is applied as forward bias, current flows in the collector circuit. The
Yeah, this is the animation I want to see.
switch is on, and there's an output. When the input signal is reversed, the emitter is reverse biased, so there is no current flow. The switch is off. Though it looks like one, this is not a common emitter amplifier. It's a direct current switch. When the switch is on, the IR drop across its load cancels the collector's reverse bias.
The IR means the resistance, the impedance resistance. So if this is a light here, it would be glowing because there's things across here. And if you actually felt that little piece of wire when this was on, it would get warm.
With no voltage across the collector junction, the transistor itself uses up almost no power. When the switch is off, there's reverse bias on the emitter junction. And without forward emitter current, no current can flow through the collector.
So because you don't have to heat an element here like in the tube, that's why a big reason why transistors are way more energy efficient. You don't have to make the tube. You don't have to like light a light bulb for every single one of these times you just want to have a switch.
With no current, no power is consumed. So whether the circuit is on or off, there's no power loss. It's practically a loss-free switch, as efficient as a night switch.
And that's why they swapped them out so quickly. As soon as they discovered this technology and how to do it and how to make them reliable, they were like, let's get rid of all these tubes. And they got rid of them fast because they're like, this is obviously better. And this is going to show what I'm talking about. Oops, not that one. The differences in how tubes and resistors.
In the previous video,
tubes and transistors behave a little differently. And yeah, okay, so let's go ahead and let him talk.
In the previous video, we took a look at what exactly vacuum tubes are and the basic principle under which they operate, which is thermionic emission. We also took a look at the most...
The thermionic emission is when you heat thermal. When you heat that element, it gives off electrons. That's called thermionic emission.
simple of vacuum tubes, the diode. And we actually played around with this little 5642 diode. And even though it's rated for extremely high voltages on the order of kilovolts, we managed to get it to work with just 24 volts, which I thought was awesome. It showed that vacuum tubes are a lot more flexible than I had initially expected when I was a kid. And we're starting to see that we can do a lot of really interesting things with vacuum tubes at low voltages. But a diode is just the beginning. There's tons of other types of vacuum tubes. And today I want to take a look at probably the most ubiquitous of vacuum tubes, and that is the triode. Just so happens that I have one right here, and this is 6DJ8. It's actually a dual triode, so there's two triodes inside.
That was that video we first saw with the tubes. Is this the triode with the cathode at the bottom emitting the electrons, and then the grid, or it causes them to stop or go through, and then it goes to the
out of here. But what is a triode, and how does it differ from a diode? Well, let's hop back over to the bench and take a look in more detail. First things first, let's just go ahead and redraw our diode from last time. So if you remember, we have a heater element on the bottom, and then we have a cathode that sits just above that heater element, and the heater heats that up. And the heater element itself is attached to 6.3 volts. And then way above the cathode here, we have a plate. And we attach the plate to a pretty high voltage, and then
that's
our cathode down here to our low side, and then we can create our diode circuit that way. Now, if you remember, as the cathode gets heated up by the heater here, it starts to throw off little bitty electrons. And these electrons really want to get up to this plate up here because it has a positive charge. So they fly up that way with a really high speed to be attracted to that plate. And that's how we get the flow of current through our circuit. Now, this is a diode, right? And so diode has, spelled like this, D-I-O-D-E. And in the beginning of diode, we have Di. And this is kind of telling us what's going on here. So Di stands for 2. So you can see that we have 2 elements inside of this. We have 1, 2. And ode is just a really short way of saying electrode. So this is a dielectrode. So we have 2 electrodes inside.
Now, we've seen these are all can be connected together. They can be separate out like this. The fact is that the thing gets hot, it starts spitting out electrons. So that is what's it's so crazy. That's all it is. And the only reason we didn't have it sooner is because someone didn't know that we could enclose them in these bulbs and have them, give off this effect. It was like there's only like a few guys working on these things. It was really nerdy. It was like, what are you guys doing over there?
Of our vacuum tube.
So there wasn't a lot of people like, oh, how can we fix this? It was sort of like, okay, this is curious. Like, oh, we can make it. And then you got the sales guys get a hold of it. It's like, we can make this work. And they just build out that technology to the maximum level as fast as they can, making money, of course. But, they're not really interested in the latest thing because they don't know if it's going to work or not. It's just scale, or it's not all guys working on it. It's that kind of thing.
Now, when we say something like triode, well, we can kind of figure out what it means, because tri means 3. So that means that there must be a third element inside of our vacuum tube. And there is, and it's called the grid. And it sits right here in the middle, in between our cathode and our plate. And the grid's job is to either let these electrons pass or to block them from going past. And we do this by controlling what kind of charge we put on the grid. And
All right, that's that switch over here. This is this thing right here. Whether we put a charge on the grid or not. All right. So keep going.
so if we have a strongly negative charge on the grid, opposites attract and like charged particles repel each other. So if this has kind of a negative charge to it, these electrons are going to get up to here and they're going to go, nope, no thank you, and they're going to turn around and head back. And so they don't
Yeah, it actually deflects all around that thing. So so if there was like, if they had another wire over here, it would be like bouncing off that. I'm not sure if it would it would like go up this way if it was on the other side. I think it would probably would. So, but it's trying to eliminate all around it. It's not just going one direction. It's like a force field going, no.
really have any place to go. And so we end up in a situation where there's no current flow through the tube. And then if we change this grid charge to a more positive charge, it starts to let more and more of these electrons through so they can make their way up to the plate. Now what's really interesting about this is that it's purely analog. So if we have a highly negative charge, say something like minus 10 volts, no electrons can get through. But then if we bring that down to say something like minus 8 volts or minus 6 volts or minus 4 volts, as we get closer and closer to 0, it starts to let a few more electrons through, more and more and more and more. And then when we get to 0, and then even up into the positive voltage range, it starts letting all of the electrons through. And then we've got a full circuit, so we get the full power through the circuit.
All right, so that's how. Wait, he gets into it here. Where is it? He gets into the differences and he shows them off with a demonstration. So that was a review of how triodes work, and he sets it up with this. He sets up this triode here with this little rheostat, which is like a little variable resistor, and he's going to show the difference between the saturation
plug in our power supply here,
transistor right here, and how the triode works. So we're going to show the differences with how they behave. Here we go.
We'll turn the power supply on. It is set to 24 volts, just like before. Now you'll notice that both of these LEDs came on, and that's because the vacuum tube itself is not warm yet. And when it takes a while for the heater to warm up, oh, hey, look at that. This LED turned off. So that's good. That means that we had something going on with our potentiometer here. So
that means that light had warmed up enough, because he's warmed up enough so it started to give off electrons. It takes a while. It has to warm up first.
that's actually off. That's keeping that off. And so what that must mean then is that we have positive voltage coming through the potentiometer to the input of both of these. But we'll take a look at that in a little more detail in a minute. What I really want to focus on right now is the button on the other side. And so you'll notice that our LED is on. And you'll also notice that I have these voltage drop resistors in parallel to the LED. And we'll talk about why I did that here in a minute after we experiment with the actual vacuum tube. So if I press that button, we should see that LED turn off, because that was, when I push that button, we put a positive voltage into the grid, and that should pull our output low. So let's try that. Let's see what happens here. Awesome, the LED turned off. That is amazing. So we have it actually functioning on and off like that. That's very cool. All right, so you can see in this way, I'm using just a 6-volt input to control our output here, and that's what I'm showing with the LED by pushing this button. All right, so that's really cool. We know now that we can use the triode as a voltage-controlled switch. But what about this potentiometer? Well, to keep our focus on just the triode for now, I'm going to remove the LED here. And as I turn this potentiometer, I'm starting to decrease the amount of voltage going into the grid. And you can see right there, we already have the LED lit up, but it's really, really, really dim. All right, so this means that we're starting to cut down the number of electrons that are flowing through. And if I rotate it more, the LED gets brighter and brighter and brighter and brighter until we hit maximum brightness. And when we hit maximum brightness, what this means is that we have the grid pulled to ground. And so all of those electrons that are trying to flow through the triode can't. And that means that our output is going to be pulled high because current can't flow through the triode. So that's really cool. We saw a very linear change in the brightness of the LED with the rotation of the potentiometer. That's very cool. We're controlling the LED's brightness. That's awesome. All right, so what about this transistor? I mean, it's set up pretty much exactly the same. So we should see a pretty similar result, right? All right, so here we go. Let's go ahead and rotate the potentiometer. All right, well, you can see that the triode LED is starting to illuminate, but the transistor LED isn't on yet. It hasn't actually illuminated at all. The triode LED is getting brighter and brighter and brighter, but this LED is actually still off. If I go a little bit brighter, whoa, look at that. The LED came on to full brightness with just not even a 16th of a turn. If I go back, it turns right off again. So what's happening here is we're seeing a very clear difference between digital and analog. So you can see that analog gives us a pretty accurate representation of the input voltage on the output, whereas with digital, with our little silicone transistor here, we're seeing it operate more like a light switch. You can see that LED comes on and off really quickly. Now, if I'm very careful with my fingers, I can kind of get a half brightness out of that LED, but it's really unstable and the LED tends to flicker. And the transistor doesn't like being in that half on, half off state. It seems to really want to go into full saturation or completely off. And so this is very interesting. This is one of the primary differences between digital electronics and analog electronics, and that's awesome. And so we can now see that we have something that we can use this triode for. We can create all sorts of really neat analog circuits with it. But remember I mentioned these little 10,000 ohm resistors. Now if I go through and I remove these from all of the LEDs here, that LED right back in place there, and then we'll remove this one. Well, you'll notice that something has changed right off the bat. The LED from our triode that's being controlled by the potentiometer is illuminated now. Now, if I move the potentiometer, you'll notice it does get brighter and it does get dimmer, but it doesn't actually ever go off. And if I push the button for the other triode, you'll notice it gets dimmer as well, but it doesn't actually go off. That's kind of weird. If we look at the transistor, we notice that the LED is completely off, and we turn it that way, the LED is completely on. And actually, now we look at it a little closer, we can see that the transistor LED is actually a little brighter than both of the triode LEDs when they're supposed to be at full brightness. So what exactly is going on here? And well, that requires us to kind of dive a lot deeper into how the triode operates. And
yeah, so you can go look into that. But that's just want to show you, like, there were some things they had to work out. But for using digital electronics, it became very clear that transistors, because of the way they behave, were the way to go. And that's like and that's why they took over almost immediately. You can use a transistor to represent any logic state. So same thing with the relay, same thing with the vacuum tube. Okay, so let's see here. So how do computers remember? This is how we build a memory up from transistors.
Hi everyone. I've recently been trying to learn a bit about how computers work, and in a previous video I explored things like representing numbers in binary and using simple logic gates to build something capable of doing addition and subtraction. What I'm interested in today though is how a computer is able to actually remember these numbers that it's working with. The light turns on. What's interesting about the little diagram I found.
So here we go. He's making a flip-flop. This is like the just a curious arrangement, clever arrangement of transistors to then act like a little piece of memory. Here we go.
So I've begun by creating this simple circuit following a little diagram I found online. If I take this red wire and connect it up here, the light turns on. What's interesting though is if I then take the wire back out, the light remains on, so somehow the state has been remembered. The other wire, by the way, can be used to turn the light back off, and so we can think of these two wires as being the set and reset inputs to our circuit.
That is the official name it's used in digital electronics. So when you want to set the value, you do this pulse. And if you want to reset the value, you do this pulse. Interesting.
Let's switch over to the little simulation program where we...
So there's a simulation program he has, which he has built, which you can find out from his website how to set that up, and it's very interesting for beginners to play with these digital electronics without having to actually physically create the digital electronics. And although that is a great thing to do, if you so desire, it's quite helpful. But you can simulate those same exact thing with this program, and it's really great. And I recommend you go check it out.
Managed to get addition and subtraction working last episode, and try create some of this mysterious memory. So I have our two input signals here, set and reset, and together these should control the state of the output signal over here. One way we can achieve the behavior we saw is using an AND gate, an OR gate, and a NOT gate. The set input goes into the OR gate, and the reset input gets inverted and then goes into the AND gate, and you can see the signal traveling along there. Now the output of the OR gate goes into the AND gate as well, and the result of that is our final output signal. But now for the fancy part. This output signal gets fed back as the other input to the OR gate.
So this is the flip-flop. This is a standard named pattern to do memory.
Let's see how this behaves. So I'll turn on the set input, which makes the OR gate turn on, which makes the AND gate turn on, and so now our output is on. Of course, this has also turned on the other input to the OR gate, so even if I now turn the set signal off, the output remains on. The only way to change the output now is using the reset signal, so let me try turning that on. This signal is inverted, so it turns off the input to the AND gate, and so the output switches off as well. I can now turn the reset input off, and the output will stay off. This little setup is known as a set-reset latch, SR latch for short. I'd like to look at a different way of constructing this latch, which I think is really interesting, but first I'll need a new building block, which is an OR gate, followed by a NOT gate, making what's called a NOR gate. Here the output is only on when both inputs are off, so if I turn either of these inputs on, the output will switch off.
So he's just making a new gate. It's just the real official thing called NOR gate, which is just the OR, and then you invert the output.
I'll just up here and then make it into its own little chip. Okay, so here we have our set and reset inputs once again, and what I'll do this time is take two of the NOR gates and feed the output of the first one into the input of the second. Both inputs of that first NOR gate are unconnected, which the simulation just treats as off, and so its output signal is currently on. This will cause the output of the second NOR gate to be off, and I'll wire that up to the input of the first one. I'll also connect it to the output signal over here, and finally I'll hook up the set and reset inputs like this. So let's try.
Isn't that neat? So it makes it like an infinity symbol here. And I did also have an example of what happens when you link this stuff up.
Set input, which will make the output of this NOR gate turn off, which then makes the other NOR gate's output turn on, and so our output signal here goes on. We also have this signal traveling along here, which we can think of as essentially locking this output into an off state, so that it remains off even if we now turn the set signal off. And so, as you can see, the output here has remained on. Let's try turning on the reset.
So it's just a different, he refactored from this first example to this example. The behavior looks the same, he just changed the implementation. This happens a lot in computers, a ton. There's always another way where you wanted to have the behavior do the same thing, but how it's actually doing it, we'll swap it out. And there's no actual behavior change, just how we're doing it makes it like for this example. This really makes it obvious. It simplifies this arrangement. It makes it see what's a more efficient way of looking at things.
No. So this will switch off the output of this NOR gate, and as a result, the output signal here will go off. That also means that this signal along here is now off, allowing this output to come back on, which then again locks the output of this NOR gate into an off state, so that even if we turn the reset signal off, the output remains off. This setup looks really simple, but it can definitely take a little while to wrap your head around what's going on here.
Yeah, I recommend doing it, but this animation really just shows in detail like what's really good, and he starts building it up for doing even more, like what happens here. So yeah, so you can go explore more about that. That's all I kind of wanted to show you, how the logic powered the electricity travels through these gates and through these transistors to build up this complex behavior.
So if we want to build some kind of output display
Here's our friend Bean Eater again, and what we're doing is we're going to be
for a computer, we can.
Here we go.
So if we want to build some kind of output display for a computer, we can use a register, just like we've built in the past, where we can push a value into that register and then have some way of displaying the contents of the register, and this would be the output of the computer. So in this case, you can see we have a nice binary output.
And we'll get into how that works.
For the computer. But what would be much nicer is if when we put contents into that register, instead of getting a binary output, we get a nice decimal output like this, which is much more user-friendly. So let's take a look at how these display modules work. So you can see there's some pins on the back, and then of course our display here. And here's the data sheet that comes with it, or I guess just sort of the packaging. And it comes in a couple different kinds. The one that I have is blue, and it says common anode. What that means is that there's a bunch of LEDs inside this package, one for each of these different segments, and all the anodes are tied together. So that's the positive side of each of these LEDs are tied together, and on pins 3 and 8. So pins 3 and 8 are just the middle pins on both sides. This is pin 3, and then this is pin 8 here in the middle on the other side. And then the rest of the pins just control the different segments. So we can hook this up on our breadboard, and I'm going to connect the anode, this is the common anode, which is either pin 3 or pin 8, to our 5-volt supply. So this is pin 8 up here.
So all the lines on the breadboard are connected up in these lines here, and he eventually wires all this thing up to, and it shows how those segments all work and how they're all built up from the ones and zeros and this pattern here on these 7 segments. And he goes through and explains how you can build these gates up to output the particular segment is for binary coded value coming in here. And we're going to get into how this all operates. I just wanted to give you a little preview and how complex these things can get to do different types of behaviors. Yeah. And you can go explore some of more of this stuff and how these things work. And the next one, we're going to be talking about the IC, which is really exciting because it allowed us, instead of doing all these wires and all these things, we can actually use photographs to build these devices up. And we'll be talking about that next one.